Right, this last section of Chapter 6 is dealing with population growth. It ties in nicely to Section 6.4, exponential growth and decay. It's not going to be a long lesson. We're going to take a look at how to derive the equations that we've been seeing in the past and just go through one example. But just reading over this, a common way to model population is with a differentiable function where the population is growing at a rate. So again, there's our derivative that we'll be writing that is proportional to the size of the current population. So again, writing this in symbols, instead of the dy over dt that you saw yesterday in section 6.4, this will become dp, where p is the population function, over dt. So the rate of change of population with respect to time is going to equal k, which is our constant, times our current population. So this is identical to what we were looking at yesterday, just using slightly different variables. We're going to solve for this differential equation in order to find a function p of t. Once we have this, again, we always want to start by writing this out, and then it leads to some function p. We do not have to show the work that we're going to do right now every single time. So we're going to use the process of separation of variables. And I want to divide both sides by p, so we're going to get dp over p is equal to k times dt. Again, it's the same process we went through yesterday. We'll integrate each side. Once I can get the screen to work. All right, so we'll take the integral. We'll have 1 over p dp is the integral of k dt. So this will give us the natural log. Now, any population function should be positive. So for this, I am not going to put the absolute value bars. So we'll just have the natural log of p plus our first constant over here. Again, k is a constant, so we get kt plus the second constant over here. So the natural log of p is equal to kt plus, when we combine these two constants here, we'll just say it's c. Next, we'll take e to the natural log of p is equal to e to the kt plus c. I'm just going to kind of stop for a second here because I've been going over this enough, but just pause and ask yourself, what do you think we could do with this e to the kt plus c to proceed to the next step? Over on the left side now, we'll just get a p, and we could rewrite this as e to the kt. So I hope you guys were thinking that we could just multiply e to the c. And again, what does e to the c become, or what have we been writing? Before we were writing an a, which we are going to leave it that way. So we could say that this is just going to be a. So now this becomes a e to the kt. So again, that matches the same format, only now we're going to look at this as p of t, because that's what we were asked to find. Instead of a, I'm going to write this in a notation to represent the initial population, and then e to some rate here is what k is going to represent. So e to the kt. So this is our population function, and again, p of 0 is our initial population. So same formula, we just went over again how to derive it. We're not going to have to do it every single time. However, with each of our problems, if it starts off a certain way with the wording, we're going to first write that dp over dt is equal to k times p. Now, in our certain problems, k might be replaced by an actual value. So if it does tell us to represent this situation with a function, if it gives us the rate, we're going to substitute that in. But then we can say that this differential equation will turn into p of t is equal to our initial population times e to the kt. So we could just show that this differential equation implies or leads us to this function. So what we're going to take a look at is page 348, number 20. I have it copied here. A honeybee population. Go ahead and pause it and just read it to yourself for right now. All right, so what we're given here is a couple bits of information telling us what the rates are. If you notice, there's two different rates depending on the size of the population. Overall, though, we are asked what we need to find is the total time for the population, I'm just going to abbreviate that here, to go from 5,000 bees to 25,000. All right, so what we're first going to look at, break this into two parts. I'm going to first say part A, we're a population when there are no more than 10,000 bees. Our rate is 1/4 the number present. So our rate, or our K here. So what we're first going to write out here is that dP over dt is going to equal 1/4 P. And then we could say that this is going to lead to a function. P of T is equal to our initial population, e to the 1/4 T. And now what we could say is we know we are starting at 5,000. So P in this case is going to be, or P naught is going to be 5,000. So now we could say we want to go, we have to stop it at 10,000 as sort of our first leg of, part of the problem here. So we're going to say an initial amount of 5,000 is going to turn into 10,000 when it's done. And that's at a rate of 1/4. So we get 10,000 is equal to 5,000 e to the 1/4 times t. Now these problems, we're just going through them as we did yesterday. Divide both sides by 5,000. So we'll get 2 is equal to e to the 1/4 t. We'll take the natural log of both sides. So we get natural log of 2 is equal to 1/4 t. Now here we're going to multiply, so t is going to equal 4 times the natural log of 2. And we're going to leave it in exact form for right now, but t is in the number of years. So that's for the first part. And for our second part, next it says if there are more than 10,000 bees but fewer than 50,000 bees, the growth rate is equal to 1/12 of the number present. So our second part of the problem, we'll say between 10,000 and 50,000. The rate is 1/12. So now, in this case, we're going to say dP over dt is equal to 1/12 P, which leads us to a function. P of T is equal to our initial population times e to the 1/12 T. So here, even though it's between 10,000 and 50,000, we just want to stop it at 25,000. So now our end amount, after a certain amount of time, is going to be 25,000. The initial amount, not the 5,000, because then that would be putting us at a rate that's between the 5,000 and the 10,000. We need to say that this is now 10,000 because that's where we left off, and we're okay as long as we're between 10,000 and 50,000. Even though it's equal to it in part A, we could still start it off here at part B. Our rate is going to be 1/12 e to the 1/12 t. So we're going to divide both sides by 10,000, and we'll get a 2.5 is equal to e to the 1/12 t. Take the natural log of each side. So we'll get natural log of 2.5 is equal to 1/12 t. So t is going to equal 12 times the natural log of 2.5. And again, that'll be in years. So we need to add both of these answers together because, again, it was one rate during the time it grew to 10,000 and a slightly different rate when it grew to 25,000. So then our answer, I'll kind of go back up and call the first part for part A the first time, so t sub 1, and then I'll call the next part t sub 2. So the answer comes from adding the two times together. And if you go ahead, if you want to pause this right now, type this into your calculator, but this will give us 4 times the natural log of 2. Plus 12 times the natural log of 2.5. Should be approximately 13.768 years. All right, so we're just taking the same types of problems that we saw in 6.4. 6.4 and 6.5 are very close together, just using different variables here to represent it, but essentially it's the same thing as we're setting up, whether we know an initial amount, a final amount. Each one is going to have slightly different information, but we always want to start with this differential equation, taking us to this function here, and then filling in what we have. Each problem, again, is going to have a different piece missing, and that's what we need to figure out.